I'm excited to get the opportunity to speak with you all tonight. So as Aleska said, I'm Alyson Wilson. I am at North Carolina State University, and I have two affiliations at the university. So I'm a statistician, so I'm a professor in the Department of Statistics. But for about the last year and a half, I have been working in the North Carolina State University Office of Research and Innovation, where some of you who are in my directed study, I do a lot of work helping other faculty at the university have the opportunity to develop a wide range of different grants and projects that they might want to work on. And so tonight I'm going to talk to you about a couple of things. So the first thing, I will be spending a little bit of time talking about what it means to be a statistician, or at least what it has meant for me to be a statistician. I think a lot of people, when they think about statisticians, if they have any idea what statisticians do, they might think about a statistician who works with a sports team, for example. And so I want to give you some examples of the kinds of things that I've had a chance to work on. And I'll do that. We'll actually go through an example of an interesting problem that I worked on, just to try to make it a little bit more concrete. So let's get started. I will say that during my lecture, I am going to ask you to have access to a browser. And so hopefully that will work for everyone. And so we're going to do a little bit of preparation before we get into the lecture. So the first thing is something that you can either do analog or digital, depending on what works more easily for you. I need you, if you've got a coin in your pocket or your purse and it's nearby, pull out a coin and flip it twice. And I want you to remember the two flips in order. So what that means is heads, tails is different than tails, heads. If you don't have a coin, that's okay. There's actually a nice website online that you can use to virtually flip a coin. And the virtual coin flip you can find at www.random.org/coins. And I'll put that in the chat for everybody. Okay, so I'll give everybody just a minute. So either actually flip a coin, or if you can't find a coin, because I know everybody doesn't have change in their pockets, take a second and go to random.org and flip your coins virtually. And again, I need you to flip twice and remember the flips in order. I would say one feature of being a statistician is one of the apps on the front page of my phone is I actually have a coin flipping app on my phone. Okay, so hopefully everybody's ready, and we'll move on to the next bit of preparation that I want you to do. So tonight we are going to do a little bit of real-time data collection. And to do that, we are going to use a website that is called menti.com. So www.menti.com. I also have that in the chat. And so I'm going to switch over and we're going to do a practice question so you get an idea of how this works. So give me just a second and I will switch over and you'll see how this actually works. Okay, so you can see on my screen that the way that we are going to collect data is you all are going to go to menti.com and it will ask you for a code. And that code is 39198912 for the first question. And that's also in the chat. And it's just practice. So I'd like all the delegates to indicate whether you are representing a state or the District of Columbia, something from the United States, or whether you're a delegate from a country that is not the United States. And the fun part about Menti is we can all watch real time as the data shows up and it updates on my screen. So I'm going to encourage everybody to do this. So we'll give it another second. We're up to about 57 respondents. Sorry, I feel like I'm watching the bag of microwave popcorn, you know, and when responses stop coming in, we'll head back. So Franco, thanks for putting that in the chat. Okay. Okay, I'm going to head back over to my talk now that you guys have seen how this works. And we'll come back and we're going to do a couple more questions as we go through what we're working on. And so, okay. So the first thing I'm going to do is, this is a little bit of a thought experiment that I like to do. And what I'm going to use it to illustrate is a way to think about the kind of statistics problem that we're going to work on a little bit later in a bigger context. And so the first thing I'm going to talk about a little bit is how to ask a sensitive question. So what do I mean by a sensitive question? So back when I was in high school, I remember I had to take these surveys where they were trying to understand, you know, they were trying to learn more about us as students, and they would ask questions that I wasn't 100% sure I wanted to answer. Things like, have you ever shoplifted? I'm thinking, how anonymous is this survey? You know, or maybe a question like, how many of you have a crush on someone in National Youth Science Camp? If you think about it, you can see that, you know, given the situation, you might be a little reluctant, kind of hesitant to answer these questions both truthfully and publicly. Does that make sense? Okay. So there are a lot of different ways that you could potentially do this, but I want to share one that's pretty simple and you know, and show you a way that you can think about getting some interesting data. So what is a method for asking these kinds of questions? So the idea is that we're going to use randomization, which means that we are going to actually use those coin flips to decide whether or not you're answering the question. So let me explain how this is going to work. So here's the strategy. So you flipped your coin twice, and as good delegates, you remember the 2 coin flips in the order. So here's actually how this will work. So think through this with me. If your first coin flip, if the first time you flipped the coin, you got heads, you are going to answer what's called the decoy question. And I'll tell you what that question is in a minute. But this is really a non-informative question. It's not getting at the question that we actually want to learn about. If you flip tails, you're going to answer the real question. Okay, so just to give an example, we are going to see what happens if we try to answer the same question that we did our original data count on, which is trying to figure out the proportion of delegates who are from the United States and not from the United States, but actually using the randomization. So here's how it works. So remember, first coin flip was heads, you'll answer decoy. First coin flip was tails, you'll answer the real question. So the decoy question is very simple. The decoy question, if you got heads on the first one, the question you're answering is, was your second coin flip heads? If it was, you'll say yes. If it was tails, you'll say no. And the real question is, as a delegate, are you representing the United States? And you answer that truthfully, yes or no. So as you can see, we've randomized. If I were to ask you a question and you were to tell me yes or no, I don't know which question you're answering. I don't know if you're telling me about the second coin flip or whether or not you're telling me about what country you represent. Does that make sense to everyone? The randomization, if you don't tell me what your coin flips are, you just tell me yes or no, and I have no way of knowing, and so that protects you. So if it's a sensitive question, you can answer truthfully, and I don't actually know what you're answering. So let's give this a try. We're going to go back over to Menti, and we are going to do the procedure that I just outlined here. So everybody think in your head, if your first coin flip was heads, answer about your second coin flip. If your first coin flip was tails, answer about whether you're a delegate from the United States. So give me a second and I will get over back to Menti again. And so we had 42 and 32 as our original answers. So this time we're doing the randomization technique, and the code is 32344079. And so if you all can now answer using your coin flips in the randomization, we'll see what we get. And for those of you who want to click directly, Franco has also shared in the chat the link that you can go directly instead of entering the code. So we're getting there. We're up to 56 responses. We had 74 to the first question. So I'm going to wait just for another second while you guys continue to answer. Okay, I tell you what I'm going to do is I'm going to switch back and I'm going to let you guys answer for a minute. And actually, I'm just going to talk a little bit about me and how I got to be a statistician while you guys are finishing up. And then once it looks like, instead of just everybody kind of peering at the blue and the pink, we will, I'll talk a little bit. And then as that finishes up, then we'll circle back and I'll actually sort of work out how all the math comes together and how we're going to use this randomized data to still actually make an estimate. Because that's not always very intuitive. It's like, but wait, you know, how are you actually going to figure out the answer to the question if you don't know who answered the question? And so that's actually a pretty interesting thing. And I'd like to show you how that works. So, okay. I'll talk again for a minute and see if we get a few more responses. As you can tell, actually, if you take a look at what I've got on the screen, I was a delegate from West Virginia in 1985. And when I got to science camp, one of the features for me was that I kind of figured out that I liked math, and I had figured out almost nothing else about what I was going to do. And so I think that's one of the features as you have a chance to, you know, go to directed studies, as you have a chance to, no, the question is, are you going to see another screen? And it's not yet. I'm just going to talk for a minute while the results are coming in. So when the results seem like they're done, then I'll flip back over to the talk. I think, you know, I think some of the talks that you hear, people seem really laser focused. I always felt like, wow, you're a doctor and you've known that you were going to be a doctor since you were like 6 years old. And so, but what I kind of knew is I liked math, but I didn't know what that was going to mean to become a career. So I went off to college. I left West Virginia and I moved to Houston, Texas. And I went to Rice University. I know there are at least a few delegates who are going to Rice this fall. And I'll be honest, at least in my brain, I changed majors every 2 weeks. So I always took math courses. I was a mechanical engineer for a year. I was one course from being a linguistics major. I did a lot of different things. But at the end of the day, I ended up with an applied math degree. But how I figured out what I wanted to do was actually through a summer internship. And so, as Brian just said in the chat, we are still missing 14 folks who answered the original question. So I'm going to encourage you. I'm going to kind of riff for like one more minute, then we're going to move on with the math, and I'll just use the data that I have. But if you're going to answer the question, please go ahead and do it. If you have a question about how to answer the question, please put it in the chat, and we'll make sure that you can actually get it done. So as I said, I was changing majors, and I'm kind of after my junior year, and I still kind of don't know what I want to do. And my parents had moved here to North Carolina. And one of the things in North Carolina is we have something called the Research Triangle Park. And there are lots and lots of pharmaceutical companies that are based in the Research Triangle Park. And I got a job writing code for one of the pharma companies in the summer. And when you're an undergrad and you're writing code, it's not always the most exciting thing. I was basically counting things. So I was looking at studies of drugs and saying how many women were in the trial, how many men were in the trial, how many were over 25, how many were under 25. Okay, maybe this year doing drug trials was exciting with COVID, but most of the time it's a little slow when you're counting things. But one of the things that was really interesting was the work that was being done in the group while I was there. And the group was actually doing the first clinical trial for a medication called AZT. So I don't know how many of you all know what AZT is, but AZT was actually the first effective treatment for HIV, which causes AIDS. So when I was in college, if you got HIV, there wasn't a treatment and you died. And so they were doing a clinical trial for a treatment that actually was one of the first things that helped turn HIV and AIDS into something that was a chronic condition versus a terminal condition. And the light bulb went off. And I said, wait, math can answer real questions and it can make an impact on whether people live or whether they die. Can I do that, please? And so that's how I actually knew that I wanted to get into statistics. Okay, so I am going to switch back now and go back over to the talk. And we're going to use the data that you provided, and we're going to take a look at, given that we use the randomization, how are we actually going to make an estimate of the number of delegates here tonight who are representing the United States. Now, remember, we actually have the data from the first question, so we know the truth. So what we're going to see is how good an estimate can we make once we add the randomization in? And, would this be an effective technique if we wanted to ask a sensitive question? So let's take a look at how we're going to do this. So the technique that we're going to use is something called a probability tree. And so here's how it works. So let's think about what we just did. So if we had the first toss of the coin, and particularly if you use the website, there was a 0.5 probability, a 50% chance that you got heads. And that meant that you were answering the decoy question. And if you were answering the decoy question, that was simply, was your second toss heads or tails? Those are each both 50%. So if you follow the upper path, the first toss was heads, the second toss was heads, you multiply 0.5 by 0.5, you get 0.25. So there's a 0.25 probability that you're answering yes, but you're answering the decoy question. And in the same way, if you threw heads and then the second toss was 0.5, there was a 0.25 chance that you said no to the decoy question. Okay, that makes sense. You flip a coin twice, so I think that all makes sense. Let's talk a little bit about how we're going to estimate the answer to the real question now. So there was a 50% chance that you would answer the real question. That means you flip tails on the first flip. And so statisticians, for things we don't know, we tend to give them Greek letters. That's how we actually refer to them. So right there where it says yes on the third line, maybe you can see my cursor. You're going to see I have a theta. That's the name of that symbol. So we're going to say that that's the probability that we're interested in. That's the probability that you say yes to the real question. Okay? So if you think about it, there was a 0.5 chance you were answering the real question, and there's a theta chance that you are saying yes to the real question. So you multiply 0.5 by theta, and the chance you're giving me a real yes is 0.5 times theta. The chance that you're giving me a real no is 1 minus theta. So again, we've got 0.5 times 1 minus theta. So the chance of getting a real no is 0.5 times 1 minus theta. Sorry for looking around. My cat's decided this is a perfect time to be loud and interested in something. And so he actually just came over to say hello. Okay, so let me pause for a minute. Does anyone have questions about sort of how this probability tree sort of breaks out the probability you're saying yes and no for the question we just did?
May I ask a question?
Absolutely.
In my 1 year statistics class I took in high school, I was taught that in order to have any statistical method like play out correctly, you need to have a large enough population. I wonder, when you put this randomizing question in, does that make the population demand even higher? I was taught that you need to have at least 40 as a population.
Yeah, and so that's actually a very good question. So the good news is that we actually had 65 answer the question. I was hoping for, maybe the slightly larger sample size. But yeah, you're exactly right. For this to work, I am making the assumptions that we have a sufficient sample size. And actually, on the next slide, I'll show you how that plays out and where the sample size comes into the calculation. And if you had some statistics, you'll actually see very specifically, not only am I going to show you what estimate we're going to use for theta, but I'm also going to show you the confidence interval. And you're going to see that it's a little wider because we actually had the second randomization. So does that sort of get at the question you're asking?
Thank you. It does.
Sure. Okay, great. Are there other questions? No, fantastic. Okay, so let me move on. So I promise I've only got like 2 slides of math, but I can't help myself. I'm a little bit of a math nerd. So how do we actually use what we just did on this previous slide? So remember, all of these things in the right-hand column. So if we think about it, the proportion of yeses that we have, who's going to say yes? There are 2 groups that are saying yes. There's one group that's saying yes, and that's going to happen 0.25 of the time because they flipped heads twice. And there's one group that's saying yes because they flipped tails first. And then the real answer to the question is yes, they're a delegate representing the a state or the District of Columbia in the United States. So the actual proportion that will say yes is 0.25 from the decoy question plus 0.05 times theta. But theta is what we're interested in because theta is the proportion who answer yes to the real question in the population. So that's what we want to get at is theta. So what we actually do in statistics is we are going to set the actual proportion. We're going to put a hat on theta to mean I'm about to estimate it. That's what the hat means. I'm about to put some data in. And that is the proportion that we expect to say yes. We're going to set it equal to the proportion who actually did say yes in the data we collected. And then we're going to solve for theta. And if we do that, we get the equation that we have down here on the bottom. So we subtract 0.25 from this proportion, and then we multiply both sides by 2, and that gives us an expression. Here's where we use the data, the proportion of yes over yes plus no. We subtract the 0.25, we multiply by 2, and that gives us our estimate. So I've been doing a little calculating in the background. And so if we look at what we got from the question that the first question you answered when everybody was just answering where they were from, we had 42 from the US and 32 non-US. And so if you look at that proportion is 0.57. So about 57% of the delegates who are on tonight were from the US. If we use the second set of data and we plug it into this equation, now remembering that everybody randomized, and so on average about half of you didn't even answer the question, the estimate that comes out based on our data of 34 and 31, notice that that's different than our original data, is the estimate that I would make there is that about 0.55. The proportion of US delegates is about 0.55. So I'm off by just a little bit, but I introduced the randomization so you could answer the question. And so, okay, so, and then the other thing that I want to show you, is let's take a look at how I would actually calculate a confidence interval for that. So what's a confidence interval? A confidence interval is just the idea that this is a sample of the data. So there's some uncertainty on the data. So, you know, when you hear about something like somebody's predicting election results, they always talk about a margin of error. You can kind of think it about that way. How much plus or minus do we have? And so in this case, and this was the question that got asked, we don't have a huge sample size. We only had about 65 folks who answered the second question. And so our confidence interval is a little wide. And so the formula that I have here is how we actually would calculate the confidence interval. And so it's our estimate of theta hat, our 0.55, plus or minus 3.92 times this expression. So I know some of you have had a statistics class. And if you've had a statistics class, you're looking saying 3.92. That number is always 1.96 when I calculate it. So 3.92 is actually 2 times the 1.96 you might be expecting, because we had 2 randomizations because of the coin flip. And so that makes the confidence interval wider. And so if I were actually reporting this, I'd say my best guess is 0.55, but my confidence interval ranges from about 30% to about 78%. So it's kind of wide because we don't have a huge sample size and because we introduced the randomization. So like the question that we had before, as the sample size gets larger, you know, if we had all 138 delegates here and it was about twice as big, so you can see that the n is under the square root sign, I would actually be expecting, if I had twice as many, to divide the size of that confidence, you know, that plus or minus by about square root of 2, so about 1.4. Okay, so just for fun, I think I'm going to ask one more question because, you know, the question that we asked wasn't particularly sensitive. So just for fun, I'm going to switch over and ask you all to use your data and use the coin flips and do one more question for me. And so I think we actually will do the crush question. So if you can go back to Menti, use your coin flips, so it's actually randomized. And the Menti code for this one is 97228127. So doing the randomization, I'd like you to answer, do you have a crush on someone at National Youth Science Camp? You don't have to have told them for it to count. That's what I mean by declared is if you told somebody, hey, I think you're cute. Undeclared is, you know, you're kind of trying to figure out what they're doing and you'd like to spend a little more time, you know, the haven't actually told them. And so, Vivian, that's a good question. Do we answer based on the coin flip? Yeah, let's do this one randomized again. So if you flip the coin, if you flipped heads, then you are answering the decoy question. Was your second flip heads? If you flip tails, answer the real question. Sorry, part of the reason why I'm doing this is I've actually done this experiment at science camp for, I think now about the last 15 years. And I'm enough of a data geek that I'm kind of curious. I actually want to collect it this year too. So, and I want to collect it under the same conditions of randomization so that we can actually get a good comparison of the results. So I'm going to let this run for a minute, and then I'll circle back in a minute and take a quick look and let you guys actually know how the results came out. Let's see. Well, you are answering slowly. Huh. Okay. I'll come back in a minute and I'll let you know how it went. Okay. So getting back over here to my slides, I thought I would actually share a picture of me from science camp. I'm guessing, can you guys tell which one is me? As delegates, I think a lot of times it's hard to tell. I'm actually the one on the left. So it was the 80s. It was the era of bad perms and parachute pants. And but yeah, that's me standing with some of the other 85 delegates. I've already talked a little bit about how I got interested in statistics. And so after I got interested in statistics, statistics by and large is a field that you typically do need some graduate training. It's getting a lot more common now, particularly in the era of data science, for students to get exposure to statistics, maybe even in high school. I'm sure some of you have had a statistics course or an advanced placement statistics course, but there aren't that many undergraduate statistics majors. So I decided I'd go get a master's degree, and I moved up to Pittsburgh, Pennsylvania, and went to Carnegie Mellon University. While I was at Carnegie Mellon, I was really interested in biomedical statistics. So I had a job over at the University of Pittsburgh, and I was working in the Department of Epidemiology, the Epidemiology Data Center. While I was there, the biggest thing that I worked on was actually a clinical trial that was one of the first looks at whether balloon angioplasty, so threading something up through your veins and then blowing up a balloon, was actually effective in helping to clear blockages in coronary arteries. Or at the time, the main treatment was a coronary artery bypass graft, where they cut you open and they took out the blocked section and they grafted something in. That was big open heart surgery. It was, really debilitating for a period of time. And the balloon angioplasty was something that was much less invasive. And balloon angioplasty did turn out to be effective. It is now actually a very common treatment when people have artery blockage. So I was getting more excited about this whole data in biomedical stuff. And so after my master's degree, I went and I worked at the National Institutes of Health in Washington, D.C. Most of what I worked on at NIH, I did a lot of work with trying to understand clinical patient care. Most of the people that I worked with were nurses that had PhDs, who were really trying to figure out what was the best way to take care of patients. So for example, one of the studies that I looked at, and this is really relevant in the time of COVID, was what is the best way when you are transitioning a patient from having a ventilator, something helping them breathe, typically, it has a tube down their throat. How do you make them comfortable and make it effective, removing that and letting them start to breathe again on their own? What's the most effective way to do that? So these were the kinds of things I was working on as a statistician. What I figured out after a couple of years is that to do what I wanted to do as a statistician, I probably needed a PhD. And what I wanted to do is, I felt like with a master's degree, I could really work on data sets that somebody had kind of seen before. The structure was the same, the way they wanted to answer the question was the same. But sometimes in the medical stuff, you got something that was a little different. There wasn't a solution that was already put together for how to analyze the data. And I wanted to know enough to be able to make solutions to solve those problems. And to do that, that meant I needed to go back to school. And so I went to Duke University, just down the road from me in Durham, North Carolina. And the problem that I worked on for my dissertation is I collaborated with researchers in the medical school. At the time, the state of the art was doing two-dimensional MRI images when you were looking at the brain. And what we were trying to do is, you can see some of the structures in the brain. We were really looking at how to understand how those varied. When you're thinking about variability, it's one thing if you're thinking about it in terms of, something that's one-dimensional. But when you're thinking about how to quantify how a shape varies, that's a little different because, a shape can vary a lot of different ways. And how do I think about it statistically? I actually spent 3 years thinking about that problem. But again, it turned out to be a really interesting thing to think about. The work that I did with my thesis ended up getting patented. And what it was used for was when people have brain cancer and they are doing radiation therapy, one of the things that you want to do is you want to make sure that they are positioned correctly so that when you radiate a portion of the brain, you hit the right spot. But if you're doing the radiation right, the tumor is changing over time. Hopefully it's shrinking as with an impact of the radiation. So being able to understand the variability and the impact of the radiation therapy was a use for actually what I had worked on. And then I started to have a life. So family reasons caused me to relocate down to southern New Mexico. I moved to Las Cruces, New Mexico, where Othello is from. And I took a job at a little bitty tiny company called Cowboy Programming Resources. I thought my PhD advisor was going to shoot me, because I've just done my PhD and it's like, yeah, sorry, I'm moving to Las Cruces, El Paso, and I'm going to go to work for a 5-person company. And what we did is we actually supported the Army doing operational evaluation of air defense artillery. So my best guess is that there might be 1 or 2 people in the audience who know what air defense artillery is or what operational evaluation is. And so let me tell you what that is, and then I will head back and I'll actually pick up a couple of questions from the chat. So operational evaluation means trying to use it in conditions that are as realistic as possible. So we were working for the Army, so you wanted to simulate combat as much as you could, but you can't actually do experiments where you shoot at soldiers with live ammunition. That's not good. So we would actually plan tests where we would take half a battalion of soldiers, so 500-600 people out in the desert for 6 weeks. We would fully script what they were doing, and we would simulate as much as possible the conditions that they would see while they were in combat. What's air defense artillery? It's stuff that shoots at stuff that flies. So you've probably seen pictures from the Middle East where you have shoulder-fired missiles that they're shooting at helicopters. That's air defense artillery. But the United States National Missile Defense System is also air defense artillery. That's a system that tries to shoot something into space to shoot down an incoming ballistic missile. So those are the kinds of systems that I worked on. And I spent a little over 4 years, actually. It was a ton of fun. I got to run around in the desert and watch people blowing stuff up and script how things were going to happen. And it was really interesting. It was also really different than what I went to grad school for. And so to circle back to a couple of the questions, so one of the things was, based on my slides, I did my PhD actually in 3 years. And how was that possible? Well, it was possible because I had already done my master's degree. So I ended up in graduate school for a total of 5 years, but I had done most of the coursework that I needed as part of my master's degree program. And so when I got to Duke, I only had 1 year of classes and I got to get started on my research really quickly. And so, so grad school is a 4 or 5 year thing in statistics. And I did the whole 5, I just didn't do them consecutively. So how much biomedical knowledge did I need to work for the NIH? So I was working in something called the Division of Computing Resources and Technology. And so our function was really to provide analytics expertise. So I was the person who knew how to use your data, could help you think about how to design your experiment. So everything that I did was in collaboration with people with very deep biomedical knowledge. I had the knowledge on the statistics side, and so together we made a good team. And so I learned a lot about biomedical things. And, of course, I had done some work at the University of Pittsburgh. So I understood a lot about how clinical trials worked, but I didn't need to, have a degree in biomedical science. I was part of a team and I brought that analytical expertise to the table. Okay. So after I was in southern New Mexico, I had a chance to move to northern New Mexico up to Los Alamos National Laboratory. We also have a New Mexico delegate from Los Alamos. And I was there for almost 9 years. So I wish I could see everybody. I usually ask at this point how many folks actually know what Los Alamos does and when Los Alamos was founded. So Los Alamos is actually the site where during the Second World War, the United States developed the first atomic bombs, nuclear weapons. This was the site where those were developed. And Karen, the New Mexico delegate from Los Alamos, actually just put a little bit of information in the chat. And so Los Alamos now is a multidisciplinary laboratory, but it still does have the mission to help maintain the US nuclear stockpile. So this is something now that the Cold War has ended, and I'll talk about non-proliferation in a couple minutes. That's something that Karen put in the chat as well. But even since the Cold War ended, the United States has not completely gotten rid of its entire nuclear weapons stockpile. And we can have some discussions about whether you think that's a good thing or a bad thing, but the way it is right now, there are the 9 nations that do have nuclear weapons, and the US has chosen to do that. One of the missions that we have at Los Alamos is we have to maintain those systems. Because, whether you think we should have them or not, there's almost nothing worse than, for example, having one go off by accident in storage in the United States. That's not something we want to have happen. We actually have to maintain them. We have to understand them. We have to understand their reliability. And that's really what I was working on. So it's a very interesting and complicated system. And actually, since 1992, when the United States decided to abide by the Comprehensive Test Ban Treaty, we haven't actually tested a nuclear weapon. So for longer than most of you all have been alive, we haven't collected any data doing system testing on these systems. So if you think for a minute, that gets kind of interesting, which is every year, the labs have to tell the president how well these systems are going to work, but we don't actually blow them up anymore. So how do we do that? And that's actually the problem that I worked on. So it isn't that we don't have any data about the systems, it's that we don't go to typically Nevada at the National Test Range and test them. Instead, what we have is we have a lot of different kinds of information. We've got information from the historical tests. We actually have some of the fastest computers in the world at Los Alamos, and we simulate down to a very small level what's happening in the systems. We bring some back every year and we take them apart and we look to see whether there's any degradation. We actually can test individual components. And the problem that I got fascinated by at Los Alamos is this problem of how do we piece that information together? How do I estimate it when I'm kind of observing a patchwork, a lot of different bits of information that I have to piece together to really start to characterize what's going on with the system? And those are really the kinds of problems that I've actually been working on for give or take the last 20 years. I'm fascinated by this problem of, so you have something that's expensive or it's complicated, how do you actually learn how it's going to work? And so after Los Alamos, I went to academic and I spent 3 years in Ames, Iowa at Iowa State. And then I went to DC and I worked for another, a little over 2 years working on science policy. And that was a whole range of questions, from problems about defense to problems about how the National Science Foundation or the National Institutes of Health or the White House ought to invest money and think about promoting science policy. And since 2013, I've been at North Carolina State and I've had a variety of jobs. And I'll tell you about sort of 2 of the things that I've worked on at NC State. So the first is actually a problem that's right in the wheelhouse of the things I like to do. North Carolina State, we actually work very closely with the United States intelligence community. So what's in the intelligence community? There are a lot of agencies you've heard of, the CIA, the National Security Agency, but they actually, like everybody else, is trying to figure out, with this explosion of data, everybody's talking about data science and all of the new data that they have. The intelligence community has this problem too, that they're able to collect data faster than they can actually analyze it. And so they made a decision to actually come partner with universities and industry to try to work on projects to help them figure out how do they use data better? How do they change analysis processes? And that's very much the kind of question I'm interested in, because intelligence analysis is very much like assessing complicated systems, you have to piece together evidence from a lot of different places to try to answer the question. So I lead the university and industry side of this collaboration. And every year we work on about 30 projects with about 10 different universities and 10 different companies, partnered up with about 50 different government staff to try to help move that forward in the intelligence community. NC State is also the home to a large consortium where we work on issues around non-proliferation. And so that's how do we prevent the spread of weapons of mass destruction, primarily nuclear, but also chemical and biological. The particular things that I'm interested in again are, if somebody's trying to get material to make a nuclear bomb, like a terrorist group, they don't usually just tweet, hey, I'm trying to buy some plutonium. Typically the problem that you're doing is piecing together many different kinds of evidence to try to figure out whether something like that's going on. So again, it's that same kind of question that I've gotten fascinated by, which is how do we make inference about questions when we don't have, probably the data that you're used to in chemistry class where you do the experiment multiple times and you actually, get a chance to do that, but where you have to put together a lot of indirect evidence. Okay. So, and as you can see, when you think about somebody being a statistician, as I said, for a lot of you, the first thought you probably have is about sports. But, I've done a lot of different problems. I've done biomedical problems, I've done defense problems, I've done, policy problems, I've done problems in counterproliferation, many, many different kinds of problems. I think for me, what I found is the kinds of problems I'm so fascinated by. You can tell I'm kind of like doing engineering problems. I'm really interested in systems and how they work and how you understand them. Sometimes those are actually physical systems like a plane. And sometimes those are sort of analytic systems where you're trying to understand how you're answering questions. And what I found is there are a lot of different places that I can work that I can do that. And I get to work on these big, hard, interesting problems with lots of collaborators and still bring my expertise, which is how do you work with data? How do you make inference? How do you put things together? So let me give you an example of one of those kinds of problems. This is a problem that I worked on for the Department of Defense, and it's another big problem. And so here was the problem. So one of the things that the United States actually has fielded is an air defense system, and it's called the National Missile Defense System. And so this is deployed primarily on the west coast of the United States. And the idea is that if somebody shoots a missile at the United States, what we will do is we will shoot a missile at the missile, and we will try to hit it and destroy it. So why in the world would we do something like that? That doesn't sound very intuitive because missiles move really fast, and then I have to get another missile to exactly the right place and hit it. Well, the idea there is that we want the actual kinetic energy. We want something moving as fast as a missile to hit the other missile because we want to make sure that we destroy the payload. Because if that payload is a chemical weapon or a biological weapon, we want to destroy it all above the atmosphere so that we don't actually have any of it filtering down as a result of the intercept. So what I was actually working on, interestingly, was I was working on designing the test part of this. So we had the National Missile Defense, but you have to test it against something. To test it, you need to fly a ballistic missile. Now, it'd be really nice if, the North Koreans would sell us a few that they were going to shoot at us so we could actually practice on the real stuff, but it doesn't work that way. So we actually have to build them ourselves. And we reverse engineer them. And it's really expensive to build one of these systems and to take it and to fly it and to test it. That entire test actually runs about $100 million. And so, yeah, I was surprised too. It's a lot of money. And so the thing you can't do is when you actually go to do the test, the system that you're going to shoot at, it has to fly. And so, I put some of the requirements of what we're doing here. We're flying something that's very complicated. They're really expensive. So we're going to fly probably one, maybe two. So it's kind of a one-of-a-kind system. It's probably similar to something we've done before. The United States builds rockets, we build missiles. So we kind of know how they work. but it's an expensive test. So the system we're building, the nice bureaucratic way to say it is high reliability is desired. What that means is it better fly because it's expensive and you've only got one. And you basically don't get to build a few and work the kinks out. You have to know it's going to fly when you actually build it. So how do you do that? It's a complicated system. And all the ways that you think about it is let's do lots of tests. Let's estimate how it's going to work. You can't really do that. So when I started working on this, my part of it was not to engineer the system, but to help them figure out how to understand whether it was going to work. I needed to estimate the reliability of the system. So how are we going to do that? So the first thing I did was I asked them, so how does this thing work? And I laughed because you figure, you ask an engineer how it works, you're going to get a very technical description. I didn't. I got a PowerPoint chart. Actually, literally this PowerPoint chart. And so, and I kind of looked at it and said, okay, so, if you look at it, you start over on the left and, you're going to have boosted flight. And then at a certain point, the fuel booster's going to come off. It's going to fly. And at a certain point, it looks like it's going to maneuver a bit. And as we get closer to apogee, the top of the parabola, we're going to deploy two things. So the gray rectangle is the reentry vehicle. That would be the thing you actually want to shoot at because that's where the stuff that explodes is. For this particular flight, the green was actually an instrumentation package because we actually wanted to watch what was happening as we got close to intercept. So we deployed cameras. It got to apogee. As it came over apogee, the remaining part separated out and we had additional auxiliary experiments deployed. And then including some of those auxiliary experiments, one of the very common countermeasures is to actually deploy several things that look like the reentry vehicle, several things that look like the explosives package, so they don't actually know what to shoot at. And so this is the slide that I got. And so what's the first thing you have to do? You have to turn that into something you can do some math on because I can't do much math on a PowerPoint picture. So what do we do? The first thing we actually did is we started to draw, this particular diagram is called a reliability block diagram. It's really starting to capture in words and actually starting to sequence in time what's happening through the flight. And you can see many of the things I just said. You've got to have ignition. It's got to fly. That's boosted flight. You've got to do some data collection because this is an experiment. The reentry vehicle has to get to apogee and it has to come back in a reasonable way. And then you also want your auxiliary experiments. So this is getting closer. I can't quite do statistics on this yet, but I'm getting closer. And so what am I going to do, though, to understand what's going on? Well, suppose that I'm thinking about ignition. What kind of data might I have about ignition? Well, the United States builds lots of rockets, and we're reusing some of the solid rocket booster technology. So I have a pretty good idea about how well that works. How have we modified it? Have we done simulations? How has it worked in the past? What do we know about how it responds to temperature changes? All of that kind of information can be brought to bear. And you've seen this about me. I love these kinds of problems. Then we start to piece together, how do we start to make that estimate? And you can start to do that across this entire range and see what you get. Okay. But there's another piece of this because, and what I just described, we actually did with the engineers. We actually took that diagram and we broke it down into a lot of detail. Eventually, that one had about 20 blocks. When we broke it down to the level where we had experimentation and the engineers could talk to us about it, it ended up having about 600 blocks on it to really fully represent what we had and to map all of the data and the simulations and the historical data and all of that. That's too complicated to brief to the general. When the general would come in, she would say, look, is this thing going to fly? And she didn't want to know that block 293, we had, some problem with the modeling and simulation. She wanted to know if it was going to fly. And so the way that typically got briefed is with something that's called a stoplight chart. And why is it called a stoplight chart? Well, because it's got red and yellow and green. And red actually means really bad. And yellow means kind of bad. And green means, close enough. And so, I said, how do you guys figure out what's really bad and what's close enough? And they said, well, it's green if I can write a press release so I don't get fired. It's like, okay. So what we ended up having to do is map all the possible outcomes into, would this really be a failure? So if the system blows up on the launch pad, that's a failure. If the reentry vehicle is wobbling when it comes back in, that's not nominal, but it's okay. Because, the countries that might shoot at us, maybe their engineering isn't fabulous. So that probably isn't that unrealistic. If we lose control of the vehicle and we can't steer where it's going, that's bad. Then I have to blow it up in the air. If I don't get all of the data collection I want, that's kind of bad because this is an experiment, so maybe that's yellow. So you get the idea that in order to actually communicate what we're talking about, we have to take all of the detailed engineering that we've got and we have to actually turn it into something a little more briefable. And this is where we come back to our idea of the probability tree that we introduced earlier. So you remember what we did when we were talking about the sensitive question. We actually did something just like that to sort of understand how this works. So we started at ignition. And if ignition was successful, we went on the upper branch. And if it blew up on the pad, that was red. And then if you had successful ignition, could you maintain steering? If the steering was a little degraded, that was yellow. If it was so bad that we had to blow it up, that was bad. And sorry, let me move forward with this instead of backward. And you can see at the end of the day, this looks very much like what we did when we were calculating the probabilities that we had. Ultimately, I'm adding up the reds, the yellows, and the greens, and rolling up my estimates so that I can actually understand what's going on with the system. So I am going to just close out for a minute, and then I'll circle back and actually do a little estimating of how many people have crushes. But statistics is actually a tool, and it's a set of methods, and it's something that really lets you dig into complex problems. A lot of my statistics colleagues kind of say, why are you a statistician? And they say, I get to play in everybody's sandbox. We get to do all kinds of cool science, and I get to work with lots of engineers. Recently, I've been working with material scientists and intelligence community analysts. I get a chance to really work on a lot of different and interesting kinds of problems. I think that you saw from where I've worked as well, it's something that I've been able to build a career, but for me, my career has been a little different than a single job. There are a lot of places that I can work on the kinds of science problems that I care about. And that's given me a lot of flexibility to move to North Carolina to be near my parents, or to, try out the faculty thing in Iowa, so that's been something that I've enjoyed a lot. The other thing that I'll mention is, why statistics? So I laugh. I have a friend who works at a pharma company, and she used to say to me that I don't care about any effect that I can't see without using statistics. And I actually think that's wrong. I think there's a lot of things that are going on that it's important to do the careful analysis to understand all of the factors that are going into what we're doing and to try to understand how things work. And if you think about the kinds of things I work on, planes and missiles and things like that, they're very complicated. And being able to have techniques and methods that let you put together lots of information is really important. And as you can tell, I think it's really fun. And I really actually believe that, good data analysis can let us do better, make better decisions. I think we actually support all kinds of different decisions about whether we should buy a system, whether this upgrade worked, whether it's safe for somebody to get on the plane, using statistics and data. And I just think that's going to increase as we increase the amount of data that we can collect. So give me 1 second. I will flip over and see what our final numbers were on here. So 31 and 27. Okay. So I will just say, Brian and I had a bit of a hypothesis that, having virtual camp would actually depress the proportion of crushes. But actually, my estimated proportion of the number of delegates who have crushes on someone at science camp is actually 57%, with a confidence interval between 31% and 82%. So actually, you guys are sort of high end over the 15 years. but the low end is usually about 45, and I've seen some up in the 60s, but 57%. So anyway,